So this is an overview of Project 12 from previous presentations with just a few additions. So just to remind everybody, this project is about designing new windows with semi-transparent PV, but with an integrated optimized performance for electricity generation, light transmission, daylight, and also thermal performance. And all three are interlinked. And what are we targeting here? At least 20 years lifetime. That's generally the lifetime of most curtain wall windows and glazings. So now to look at the bigger picture, what is happening with buildings. So some of the major international trends in high performance buildings is first of all the adoption of net zero energy as a long-term goal by the American Society of Heating, Refrigerating and Air Conditioning Engineers. That's the major engineering society and organization in which building energy designers and the whole field of HVAC and now renewables related to buildings is happening. So the second important trend is measures to reduce and shift peak electricity demand from buildings, to reduce the need to build new power plants to meet that small peak, that peak over a small period amount of time. So thermal storage and energy storage in buildings is becoming very important. So that's integration with smart grids also. And the third is probably the most challenging area, how to integrate the new energy technologies, including BIPV, but also other technologies such as advanced heat pumps, control shading devices, daylighting devices like this one that reflects daylight deep into the space, semi-transparent PV, and PVT, where we generate electricity and heat from the PV. So we have new concepts now for all neighborhoods that integrate PV in a systematic way on a massive basis, but deviating from the boring rectangular designs of buildings. So actually, what we can found is that by an L shape for a house or for a building is optimal in many ways when you look at the global picture. That is electricity generation, also passive solar gains, but also daylighting and daylight penetrating deep into a space. There is the whole issue of density also and how to position the houses relative to each other. So the big picture, looking at generation of solar electricity, solar heat, storing some of it in the underground boreholes for use in a few years or in a year. So this all of these technologies coming together make it possible to achieve net zero energy on a neighborhood scale. Now looking at commercial institutional buildings, there has been quite a big evolution over the last 100 years, going from very small window areas in the 1950s driven by the adoption of electric lighting, way before that. So like this building in downtown Montreal had no windows, it's the Place Bonaventure. It had no windows and it was built around that period. They had to cut the concrete walls to put windows recently in an attempt to fix problems with the building envelope at the same time. So now we have moved to glass towers or these fully glazed facades like this engineering building at Concordia. And this is creating another problem, higher cooling loads, some other problems with failures in the building envelope. But at the same time, this is creating an opportunity for BIPV and semi-transparent PV in facades SMEs to approach net zero energy. At the same time, there is a renewed interest in more daylighting technologies and natural and hybrid ventilation. And all of these are actually interrelated. Here's an example. So the building I just showed you is the engineering building, and this is the John Mosson School of Business. So these are two relatively new buildings, and this is where we had this major demonstration project of BIPV in the John Mosson School of Business building that has been there now for about 6 years. So it is generally performing as expected, with peak generation of 25 kilowatts of electricity, 75 kilowatts of heat. These are peak. Now this is an area of less than 300 square meters. So imagine if we covered the complete facade or 60% of this facade with this technology, the possibilities are very high if it is done on a systematic basis. So this is what the challenge is now, how to systematically design new buildings like this with mass adoption of BIPV on as many surfaces as possible, except north facing perhaps, and how to optimize even the windows. You see that the motorized shades are at random positions. These windows could include STPV. So this is my house very quickly. Again, the BIPV system, as you see, has no snow. Now this is an obsolete technology, unisolar. So I'm planning to replace that in my next sabbatical with an updated version of BIPV. The big question here is how to come up with integrated concepts for housing that could possibly even include semi-transparent PV in the top portion of windows, because the top portion of the windows doesn't need to be completely clear. So you see here the roof, a close-up of the roof. So this is unisolar, and we are working on new designs that can possibly come up with combined efficiency, thermal and electrical close to 50%. So the key challenge with fenestration and semi-transparent PV is how to optimally utilize as much of the solar spectrum as possible. We are about close to half of it is in the visible range. So the challenge is to balance the need for daylight throughout the year, passive solar gains in the heating season, and the need to limit excessive solar gains during the cooling season. So it's quite a tricky thing to do. It touches on thermal comfort, views. So we have progressed significantly in Project 12, but there is still a way to go. So here you see the possibility of using semi-transparent PV shading device. Now this is the last slide. So recently we worked on a project with near Net Zero Energy building, 2,000 square meters, the Varennes Library near Montreal. So we provide input at the early design stage on optimizing the form of the building. It has a BIPV but not optimized BIPV system. Basically a simplified version of what we did before, some skylights in the roof, but the most challenging part was the facade. So again, the problem there and the challenge is how to come up with optimal facade concepts, but they touch on building operation. Because of the dynamic nature of buildings and the daylight being one of the most complex areas in building design, optimal integration is the key, and optimization of the form of the building. Actually, I'm quite happy with the shape, but we have to provide input at the early stage for this to be done. So this is an ongoing project. We will be involved in monitoring it and modeling the as-built performance. So the challenge then is optimal integration of the technologies and then operation at the same time, both control of the building and design in an integrated manner. Thank you.
Thank you. Just one question, Kevin.
Okay, so you showed a solar community where they're laying out houses for efficient solar self-generation. Now, is that an efficient use of land?
That's a very complex question. There is always the issue of density versus how high you go. There is no simple answer to that because
Just
it touches on everything from transportation, how wide you make the roads. So there is no simple answer to that.
Okay, I just asked because where I'm from, they try to basically cram as many houses together as they can, and that seems to be a growing trend, at least where I'm from.
Actually, again, in theory, yes, that's true, that the more dense you make it, the better it is. But if you make it too dense, it affects other aspects of quality of life.
Yes, oh, for sure.
So also quality of the indoor environment, the outdoor environment, yes.
Thank you.
Yeah, okay.
Yeah, Tom.
To look at this from the other side, have you looked at building codes? So I had lunch with an architect, an international architect, who said codes in Europe are much tougher than they are here. So I'm imagining that if you look at our building code and the European building code, that you could almost make a stepwise progression from one code to another. That would take us a long way to what you're presenting, but doing it through code. So have you looked at building codes and have any sense of what the low-hanging fruits are if we were to continually toughen our building codes?
Yeah. Actually, building codes tend to be more restrictive in Europe, even in things having to do with appearance of buildings, modifications to buildings. So it's easier for us here to do innovative things than it is in Europe. Some of the projects that we did here, especially with the facades, the BIPV systems, they would probably have been very difficult to do in Europe. So it's easier for us to do these things in North America and Canada and the US.
Okay, last question, Kenneth.
Okay, short one. Thank you, Andreas. Very interesting. It's progressing. And so you talked here about the angle. So the 40 degrees is what is it? So that the light slides off, or just because you want to be the same latitude so that you get the best efficiency?
It's a snow problem. So what we have found from the projects that we have done over the years is that you really need to go with the slope at least 40 degrees to avoid snow accumulation during the winter. And of course in Montreal, when you are around the latitude slope, which is 45, that's optimal for year-round solar energy utilization. So, but there is no big difference between 40 and 45. But if you go to 45, you need more materials because the roof requires more material, so it's going to cost more. So a compromise actually 40 degrees is pretty good. But if you go down to 30, then you'll have quite a bit of snow and ice collecting in the winter.